5 plus 5. I will let you know 5 minutes before the end. Thank you.
So thank you very much for the opportunity to participate in this great workshop with a lot of very interesting talks. So I will talk about some aspects of model building, in particular some systematic way to check anomaly-free abelian gauge symmetries. I will focus in the application in which this kind of of symmetries can be used to build a dark sector with Dirac neutrino masses. So I will divide the two types of abelian symmetry in the usual dark symmetry with a dark photon, under which the standard model particles are neutral. And I will call the usual multi-test set prime abelian station as an active symmetry. Under this symmetry, the standard model is charged. Here, by my convention, will be that the symbols of the right-handed fields the symbol for the charges of the right-handed fields will have the same letter of the field. For example, the right-handed electron will have one X charge E, and the conjugate of the lepton doublet will have one X charge L, and so on and so forth. So the idea is to have these two kinds of symmetries, but extended with extra chiral fields. In the case of the dark symmetry, in addition to the neutral standard model particle, we will include n chiral fields, such that there are no vector-like pairs in the set. For the case of the active symmetry, we will consider one n prime number of chiral fields that is less than in the dark case for a number of 3. So n prime is going for 1, 2, 3 until n prime, and later for the dark symmetry we will consider 3 additional chiral fields. So it is well known that in the case of the active symmetry, we can express the solution of the full anomaly condition until the linear and cubic ones in terms of 2 free parameters that I will choose to be L, the chart of the right-handed lepton doublet, and M, a free parameter that depends in some sense of the chart of the right electron. So in terms of the solution for the active symmetry, we can write the S charges as the charges of the n prime chiral fields plus 3 equal numbers. Without loss of generality, it is always possible to choose all these numbers to be integers. So I will use that convention. So typically, the solution of the active symmetry involves a set of n charges, 3 of which are exactly the same. And this can be used to express the other standard model field I will illustrate below. And on the other hand, for the case of the dark symmetry, we will have the n chiral fields that need to satisfy the anomaly condition. So in summary, these two set of integers, either with 3 repeated one or the general ones, need to satisfy the condition for the cancellation of the linear anomalies and the cubic anomalies. So as an example, I will illustrate how the same set of integer charges can be used both for U1X symmetries and for DAR symmetries. For example, this is a very well-known solution for these two conditions. For this condition, we can have, for example, this assignment 1, 1, 1, minus 4, minus 4, 5. So we can see here there are 3 repeated charges. So this, in this case, because of this feature, we can use this solution to build one symmetry. So I will choose the equal 3 charges as my free parameter M, and the other 3 charges as charges of extra single fields that I will call M4, M5, and 6. So how can I build the standard model charger from this assignment? So the right-handed up quark, the down, in general, the quarks, the lepton, and the Higgs are expressed in terms of the corresponding symbol, and these X charges can be expressed in terms of the 2 free parameters M and L. Each one of the charges depend explicitly in M. So because here we have fixed the number for N, we have the general assignment for any X symmetry. So the assignment is here. In particular, for example, here there is still a free parameter L that can be chosen, for example, to obtain the B minus L symmetry. When I choose here L equal 1, we have the usual B minus L matrix with the neutral Higgs under this assignment. So under this B minus L, these right-handed neutrinos have exotic extra charges that helps to cancel the anomaly. So the same set of solution can be also used to build a dark symmetry. In that case, all these 6 charges are used to assign new chiral fields. So with these new chiral fields, we can build any phenomenology associated with them, but the important point as the assignment also satisfies exactly the same equation. So the idea is that the same condition used for dark symmetry can be reinterpreted as a general X symmetry if the specific solution has 3 repeated charges. It is a result well known for at most 3 extra single fields. And the new feature here in my study is that we extend this kind of procedure for an arbitrary number of chiral fields. So the idea is that these kind of equations are more easily to solve than the general problem of the active symmetry. So it is better to focus only in the condition for the dark symmetry and later reinterpreting them to obtain any active symmetry. So the conditions are these one that are the 2 Diophantine equations. And recently in this paper, these people developed a method to explore all the solution more easily in the exploration of the possibilities. The idea is that instead of working with n integers, it is better to work with a set of 2 integers that have a very low, a more rather low dimension. So for example, if in the previous case, I have 6 charges. So instead of trying to use the force brute to find 6 charges satisfying this, we can focus into use 2 sets of 2 integers, L with 2 integers and K with 2 integers. And with these 2 integers, we can build the following. For example, we can find one trivial solution X with n fields by using vector-like solutions. For example, these L1 and L1 and minus L1 are vector-like, K1 and Ky are vector-like, and so forth and so forth. And also I can build this another vector-like solution. So this is for the case of n even. There is also one assignment for n odd that involves a different dimension, but also very low. So when you have this trivial solution, you can build a more general solution by this operation. And this operation, in addition, can also give us a chiral solution. So the idea is to search for the chiral solution through this straightforward procedure. To implement this method, we create some Python package that can be installed like a normal Python module. And for example, here one installed, we can check, for example, the one example with 6 integers for which we can use, for example, this list of 2 integers, -1, this list of 2 other integers, 4 - 2, and use this function free with the 2 set of integers and obtain a no trivial solution. And this solution, after some simplification, turns out to be just the standard one that I presented before. So once with this implementation, we can explore a full set of values. For example, in this case, I start exploring a very large range of integers with a very wide possibilities for maximum values. And with this exploration, I got around 9 billion solutions, 1 billion solutions. Here, we restrict here the case in which I have 2 repeated charges that can be used as I will illustrate later for right-handed neutrinos. So the solution are at least nu, and more extra integers, so with 2 equals. So this condition reduce the number to around 20,000. It is still a lot, so I need to impose additional phenomenological condition to have a more restricted set of solutions. So what kind of phenomenological conditions I will be used here? So I will study the generation of Dirac neutrino masses at one loop with topologies that requires chiral fields. So these S1 and X2 in these topologies are chiral fields. The chiral field means that the fundamental masses are forbidden, and only the, excuse me, puede media hora. Sorry for the interruption. So here we have the chiral fields acquiring a mass from the Baryons speciation value of the singlet scalar. This singlet scalar is the same that breaks spontaneously the Abelian symmetry. So we only allow for masses generated this way. Once you have this singlet scalar, you can also have dimension 6 diagrams like this one. So they are also automatically taken into account. So for one specific realization, we choose, for example, in this topology, a lepton doublet here, the right-handed neutrino in the other side, and here we require a doublet scalar, a singlet scalar, the standard model Higgs, and here we have the 2 chiral fields that will appear in the anomaly cancellation. I will call them XR and XL, and I will assign the charges R and L respectively. And for right-handed neutrinos, I will focus on this assignment nu. So the solution that I will be searching for are a set of integers that have some R integer associated with one of the chiral fermions participating in the loop, one R char for the other component of the chiral pair that will acquire a Dirac mass, and at least 2 right-handed neutrinos, because 2 right-handed neutrinos is enough to explain all the neutrino oscillation data. Optionally, the solution can have a triplicated charge, and in that case, in addition to have a dark symmetry solution, we can also have one active solution. So this is the idea. In general, we need to impose the phenomenological conditions in a general way in order to search for all the possibilities. So in that case, for example, for the topologies with dimension phi, we have a very general condition that is just these three charges that are already defined to be equal to 0 in the case of the dark symmetry. While in the case of the active symmetry, we need, in addition, to introduce the m parameter that give arise the full condition now. So we have then the possibilities to have either, for example, a solution of the Dirac neutrino mass with a Dirac mediator and a dark symmetry, or also a Dirac mediator inside an active symmetry. In the first case, I will call the solution the dark Dirac mediator, and in the other case, the X Dirac mediator. And for the other topology, it is possible to use also a Majorana mediator that also acquires a mass through the spontaneous symmetry breaking. And in addition, we will then have the dark Majorana mediator solution and the active Majorana mediator solution in both dimension 5 and dimension 6. When we, let me just refocus here. For dimension high, I have the Dirac mediator solution condition there, and here are the condition for, let me check what happened here. Yes, this is, sorry, this is wrong here. Sorry, this is dimension 5, this is the condition for dimension 6, and this is the dimension 5, this is the condition for dimension 6 with Majorana mediators. This is Majorana mediator, and this is our Dirac mediators. So at the end, I will search for this kind of patterns in my solution. Two equal charges to be identified as the right-handed neutrinos, two pairs to be identified with the Dirac mediator, and for the active solution, maybe I will search also for solution with 3 repeated charges. While in the case of Majorana mediator, I will only need one extra chiral field with some specific condition given by either of the two possibilities. So after impose this kind of phenomenological condition, we have a set of unique solutions. This kind of unique solution are associated either with a dark symmetry or with one active symmetry. In the case of the dark symmetry, we can have either a Dirac mediator or a Majorana mediator. This is the solution with the Dirac mediator and with Majorana mediator in the case of the dark symmetry. And similarly, for the case of the active symmetry, we have also the two possibilities, a Dirac mediator or a Majorana mediator. So with this filter, we end up with around 80 solutions by imposing the restriction that only two massless states are allowed beyond the ones used for the solution. For example, in this case that I have resulted here in red, there are no massless states at all. These are the two right-handed neutrinos that acquires the mass radiatively, and the other two pairs of numbers acquires Dirac masses. For example, this -2 -3 coupled with a singlet scalar of chart 5 and acquire a mass, and this 1 - 6 also acquire mass with exactly the same singlet scalar. So in this case, we have the neutrino masses and one hidden sector with two Dirac fermions, and the lighted state of the two Dirac fermions is the dark matter candidate. In addition, we require some extra inner scalar in order to close the neutrino loop. So each one of these possibilities is one specific model. So we have a lot of different phenomenological possibilities, all of them completely valid. In some cases, some chiral state remain massless. So we can use the solution that way or introduce one extra S prime to give masses to the extra chiral fields. In some cases, for example, the solution only requires only one singlet scalar. These kind of solutions are the ones that are here resulted in red. In particular, I will focus in this specific solution because, for example, in that case, we have the three right-handed neutrinos, and we have three pairs that acquire mass with a singlet scalar of charge 7 after the spontaneous symmetry breaking, and these Dirac fields doesn't mix at all between them. So this is a model with when we have Dirac neutrino masses at one loop level and a three multi-component Dirac fermion dark matter model, in which each Dirac fermion can be an independent dark matter candidate. So the full exploration of the model implies there are many possibilities for phenomenology, both in the dark sectors models and also for the active symmetries. In particular, any model in which we can have, for example, three repeated charges like here, in which we have the X or X here, for example, here, we have three repeated charges that are here. So this can be interpreted either as a dark solution or one active solution with this assignment for the right-handed neutrinos. So at the end, we end up with a very simple solution for singlet with only a singlet scalar for both dark symmetries with Dirac and Majorana mediators, these two from here, and also a very simple solution for the active symmetry with a Dirac mediator. To obtain a simple solution for an active symmetry, but with a Majorana mediator, we need to go further to dimension 6. So this is the other set of solution for dimension 6. And here we recover one possibility for Dirac mediation and one active symmetry, because we have three repeated charges here. And we have this solution for Majorana mediator. So at the end, we have a lot of possibilities, a lot of models that need to be explored. Some of them are already studied, and previously, for example, this one from here, or from here, this is from us. This is a new analysis from this year that imply, in fact, a two multi-component dark matter candidate with right-handed neutrino mass with Dirac neutrino masses at one loop with Dirac mediators. And this was studied by us the last year with the standard solution, but interpreted as a dark symmetry.
Sorry, Diego, you have 4 minutes.
Okay, maybe I now can wrap up. So the conclusion, I presented a method to use the solution for the dark symmetry for all kind of abelian gauge solution. This method allows to use only the simple Diophantine equation that can be easily explored in a full range of parameter space. With this method, it is possible to find full set of solution once you set the phenomenological conditions. So it is very convenient to obtain the full set of phenomenological possibilities that are consistent with anomaly cancellation. Some possibilities of this method can be extended if we consider also this kind of simple equation, but in the concept of multiplets or non-universal discharges. But this is just in very early stage of exploration by now. So I can finish here now.
Great, thank you, Diego. So are there questions or comments for Diego? So you can raise your hand or just open your mic.
Nicolas, I have a question.
I can, sorry.
Diego, can you hear me?
Yes, I can hear you.
Do you explore the possible Riemann symmetries after the U1 symmetry breaking in order to stabilize the Dark particle? Yeah, Diego, you are mute.
Sorry, I'm
Diego,
back.
you're mute.
Can you guys hear me? You're muted, Diego. Sorry, I have problem with my Zoom.
Now, the question was if we explore already the Riemann symmetries, and no, we are still in the exploration of the general feature of the solution, but without any specific model yet.
And it is possible to use these kind of solutions to have sub-GV dark matter?
Yes, of course, because in the case of the dark symmetries, you have a dark photon and the usual constraints for this kind of theories of model. For example, any model what was presented before in which the dark photon were used can be easily accommodated in this setup.
Okay, great, thank you.
Okay, thanks. So a mini question maybe. We just have like a minute. So if not, let's thank Diego again. And next talk will be by Carlos Pires. Are you Carlos there?
Hi, Nicolas. Do you hear me?
Yes, perfectly.
Let me show my screen. Do you see my screen?
Uh-huh. Yeah.
And now, you see?
Yes.
Okay.
Yes, thanks.
Let's start. First of all, I would like to thank the organizer for the invitation to participate of this nice workshop and say hi to everybody that is watching us here. I'm going to talk about warm dark matter in a extension of the standard model, in a non-abelian gauge station of the standard model. I'm going to talk about protocol and constraint over this model. You know that the canonical kind of dark matter that maybe exists in the universe is hot, cold, and warm. But today, currently, you have a lot of new kind of dark matter. For example, self-interaction, fusion, black hole, and a lot of other possibilities. That's very nice. But you know that the universe contains hot dark matter in the form of active neutrino. And since the discovery of the mass of the active neutrino, they are very light. They belong to the sub-EV scale. And then they are underabundant. So this kind of hot dark matter is characterized by high velocity, which means that they have a large free stream. And unfortunately, this prevents formation of a small scale structure of the universe. The hot dark matter is not a good dark matter candidate for compose all the abundance, compose the dark matter of the universe. Well, there another kind of dark matter is very well known that called dark matter. This kind of dark matter is very popular. People has been working with cold dark matter for, I think, 3 or 4 decades. And it is characterized by negligible velocity. And in what concerns structure formation, it is a good candidate, but it's not perfect. It didn't solve all the problem with structure formation. But it's nice. People consider cold dark matter as a nice candidate for structure formation. But what is more interesting in cold dark matter is that it may be detected. It may be detected by 3 ways. That is direct, indirect, and collider. But the great disappointment is that until now, all this possibility of detection has been failed. Then this is very disappointing because I think that cold dark matter is the only way that is the only kind of dark matter, is the only candidate that can be detected. There are no other candidate. Well, I think you are going to have problem to detect them. And one of these possibilities is warm dark matter, and it is this candidate that I'm going to discuss here inside each stage of the standard model. Well, warm dark matter is also very well known since long time, but only recently it is very popular. And I think this is so because cold dark matter has been failed to be detected. Then people start to try another possibility. And warm dark matter is a very nice possibility because it is very complex. It is characterized by intermediate velocity and concern structure formation. It is so good as cold dark matter. I'm not so sure, but people that work with structure formation say that it's very good because structure formation is work only with simulation, and I, I, I never did simulation there. I cannot say how good is it, but people say it's good. So my presentation will be very simple. I will not go into the details of the computation, neither into the details of the model, because the model I'm going to discuss is very long and very complex, and is, I think, better to not present here. And the computation also are very complex. It's not nice to present here. So first, let me talk about the protocol. Okay. Cold dark matter. If you wanna work with cold dark matter, first thing to do is to find a candidate, uh, and, and present a symmetry. This symmetry must guarantee stability of the candidate. Well, once you have that, the next step is calculate the abundance. Well, calculate the abundance in cold dark matter today currently is very simple. Even if this is simple yet, this is simpler if you have cold dark matter in the form of WIMP. The abundance may be given by this expression here, but there is package that calculate the abundance, for example, micro omega. So you guarantee stability by means of symmetry, calculate the abundance, and go to analyze detection. Of course, you didn't detect, experiment didn't detect cold dark matter. Then all the data for experiment translate constraint over the model. And uh, this is really what you do with our model. So you see that this protocol is very simple. Well, it's not so simple, but it's simple when you compare with warm dark matter. When I say warm dark matter, I refer to stellar neutrino here. Okay? And when I say stellar neutrino, stellar neutrino is stellar, it's all red dark, which means they didn't interact with the standard model. The stability is complicated. How are you going to have stability since they mix with the active neutrino? Oh, the only way is that stability translates in a constraint over the mixing angle of the among the mixing among the stellar neutrino and active neutrino. You do not need you do not have a symmetry. It's a constraint over the mixing angle. This is possible because all Israeli neutrino that are right-handed neutrino, they are involved in the type 1 seesaw mechanism. And you know that from the three right-handed neutrino, only two are necessary to generate small mass for the active neutrino. And there are also observations of X-ray and Lima alpha. These you can escape from this observation by taking the mass of the Israeli neutrino above 2 keV. That's sufficient. For this point, I refer to this report of Alexander Kozenko, a very nice report concerning warm dark matter. So in what I'm going to do here, I skip this part because this part is annoying, is not interesting for my work here. I say why so soon. Then once you are sure you have a candidate, you go to calculate the temperature, the freeze-out temperature. You know how you do this. You compare the rate of interaction with the expansion of the universe. And this is necessary because you have to guarantee that this candidate is in thermal equilibrium in the early universe. And when the rate of interaction get equal to the expansion of the universe, in this point, you have the temperature freeze out. We are going to see for the warm dark matter, this temperature, this point, the dark matter is relativistic in this point, in the decoupling. Once you have the freeze-out temperature, you go to obtain the abundance. Now here is a little complicated because you do not dispose of code, computational code, as for example micro omega. You have to calculate at hand. You have to prepare a code and solve the ultimate equation. But unfortunately, when you do that, what is going to happen? You are going to have the dark matter is overabundant. Okay, overabundant. This is not a problem, but you are going always have overabundance of warm dark matter. So what you have to do to dilute this abundance, you do that by injecting entropy into the model, into the universe. The injection of entropy is by means of another particle that you refer here as diluter. You need a particle that you play the role of diluter. This particle you inject entropy in the universe and is going to dilute the overabundance of dark matter. And now you have to treat of this diluter. For this diluter I refer as to this diluter must be have long lived must be a have long lived particle, and be relativistic at the decoupling, because if it is not relativistic, it will not provide enough entropy. After that, you have two cases here. First case, okay, and this diluter must decay, and this decay it must decay after becoming non-relativist. All these translating constraint over the model, over the scenario. In this point, you share in two situations. Case one, when you do not have thermal production of the dark matter, we do not have this constraint. In this case, you obtain the necessary amount of entropy, and by end, you impose that the warm dark matter candidate be non-relativistic at the matter radiation equality. That's all for this case. If you have that, you write the paper and submit to publication. Another case is when you have a non-thermal production of warm dark matter. So in this case, you calculate when you have non-thermal production, you have to obtain the evolution of both the abundance of the evolution of the abundance of both S2 and of the candidate. Okay. Then you check if S by end you must check if the warm dark matter is non-relativistic at the matter radiation equality, and that's all for this case. At the end of this point, you write the paper and submit for publication. Okay. As I said, all these points are translating constraints over the model. Okay. The first model I'm going to discuss here is left-right model. You know that left-right model, the fermion contents, the left-hand fermion content comes in doublet, and the right-hand content also comes in doublet. But you see here that the left-right model, it has a right-hand neutrino, and the mediator of this interaction are the standard gauge boson, a new charge gauge boson that you call WR, and a new Z prime. Those are the mediator. And one nice thing of this model, it provides the type 1 seesaw mechanism. This mechanism generates a small mass for the active neutrino. But unfortunately, in this case, the right-hand neutrino mix with the active neutrino, and the mix is governed by this. The value of the mix is given by this ratio here. Okay, so you have mixing of the active neutrino with the with the right-hand neutrino, and this, in fact, this is a problem to have stability of the dark matter. So this picture here is what I really want to show for you. That's the following. Inside the left-right model, this picture I take from Lawrence Hall and collaborator, published in this year. And after all the constraints, in order for the model have a nice warm dark matter candidate, you have only 3 windows that are these 3 triangles here. What's the point that I want to call the attention here? I will take this point here, this window here, this region here. And this region is allowed, okay? You see that you are going to have warm dark matter with mass in the keV scale, but the scale of left-right model is very high, 10 to the 7. This means that the signature of the model can escape the LAC, and this is not good from the point of view of phenomenology. But unfortunately, this is the reality of warm dark matter implemented with non-abelian gauge extension of the standard model. So this is the main result of the looking for warm dark matter in left-right model. And I'm going to show now our working, our main result, that is stored the warm dark matter inside this model here. This is we call that 3-to-1 model with right-hand neutrino. In this model, the matter content, the right-hand neutrino compose a triplet of fermions. Okay, so you have the right-hand neutrino here, and the new gauge boson is a double prime, a charged prime, two new non-Hermitian neutral gauge boson, and a Z prime. These are the new ingredient of the model. Here are the standard mediator. And after the spontaneous break of the symmetry to the electromagnetism 1, the active neutrino mix among themselves, and I will refer as the physical active neutrino as N1, N2, and 3. And the right-hand neutrino may mix too, but it's not necessary. But from now on, I refer to sterile neutrino, the physical sterile neutrino as S1, S2, and S3. Okay, this model was proposed in 1994 by Plates and collaborator, and by Foote and Robert Foote and collaborator. Okay. What is interesting in this model is that the mixing among active neutrino and right-hand neutrino is not mandatory. It's not necessary. You can avoid this mix. You can avoid that because while in the left-right model, left-right model, they generate the type 1 seesaw mechanism. Inside the 3-to-1 model, the seesaw mechanism is the type 2 seesaw mechanism. Then, in face of the type 2 seesaw mechanism, the right-hand neutrino doesn't need to mix with the left-hand neutrino. In fact, there is a symmetry, intrinsic symmetry in the model, a kind of R-parity symmetry, like supersymmetry, that avoid this mixing. If you wish to have this mixing, you have to break this symmetry. That is not the case in this work. Then, from the 3 sterile neutrino, I will choose the light test 1 that I refer as S1 to be the dark matter candidate in the warm form. And S2 and S3 will be the diluter, okay? And inside the model, the relevant process to calculate the abundance is one intermediate by Z prime, okay? W prime and U0, okay? L here are the standard charge lepton. These are the neutrinos, okay? That's all you need to know. That's all you need to go ahead. And for the non-thermal production, you have this decay here. So we cannot avoid this decay. So then we are always you have the thermal production, okay? So let me go to our result. This paper, we are finished this paper. Vinicius is a master student here in Paraiba. Dutra is a postdoc in Canada, and he is Farinaldo. Okay, our result. First of all, this is the temperature decoupling. S1 and S2 decoupling practically with the same temperature. You see the couple that the couple is non-relativistic because the temperature here is more or less 10 to 4 GeV. Then both particles decouple relativistically. That's good. This behavior here is because it becomes non-relativist, and this is the behavior exponentially decreased when it's non-relativist. So you have these two graphs, these two pictures here. This picture here, this is the density, the number of density divided by the entropy density. It is constant, S to S1, S to S2. But when S2 decay, you are going to have injection of entropy, and this line here means that you are going to you have an overabundance of dark matter and S2. But when S2 decay, the abundance comes to the correct one. But perceive that you need a non-thermal contribution to take this abundance to the correct one. Okay, and this other graph plot is very interesting. In the early universe, the energy density of the diluted dominate the early universe. Then it decay. When it decay, it increases the entropy. This is the necessary entropy you need to dilute. And after that, radiation dominates the universe. This means that things is working. It's working well. It's working very well. So this is our main result. That are the constraints that come from all those protocols. The constraints, this region is excluded due to Big Bang nucleosynthesis. This region is excluded because the decoupling is non-relativist. Only this white region is allowed. And you see here, and this line gives the correct abundance for these three possibilities here. So you are going to see again that the mass of the new gauge bulbs or the signature of the model is in order of 10 to the 6 GeV. And again, this escape LHC. So that's what you can say. The model has a viable dark matter candidate in the form of worm, but unfortunately it escaped detection of the model. The signature of the model is not allowed to be reached in the LHC. So our conclusion is very simple. Warm dark matter, besides complex, much more complex than cold dark matter, it is a viable candidate for composite dark matter of the universe. The models can produce dark matter in correct abundance. But the challenge is detection and embed dark matter in a phenomenologically viable gauge theory is a challenge. Okay. Well, that's all. I will stop here. That's all I would like to show for you guys. Thank you. Where am I?
Thank you very much, Carlos. Are there questions or comments to Carlos?
I'm lost here. Where am I?
So you can raise your hand or just
I cannot see where am I
yourself.
here.
Well, I don't see any.
I'm not lost in connection. Yeah. Where am I?
Can you hear us, Carlos?
I hear you, but I don't see
okay.
you. Very strange.
Okay, so I don't see any questions. So what we can do is to keep with the program. So thanks a lot, Carlos. And next speaker is Tomer. So
can you hear me?
Yes, we can hear you.
Let me get my phone out of the way. All right.
Yeah, so I think you can share your screen.
There we go.
Excellent. Yeah.
1 second. Yeah, can you see it?
Perfectly. Yeah. Thanks.
All right. So thanks for the invitation. I don't know what about you guys, but COVID-19 hasn't been making me more efficient. And when I was thinking about what to talk about in this workshop, I realized that a lot of the things I'm excited about these days are work in progress that has been a continuation of some ambulances I chased in the past few years. So I thought that would be a nice topic to discuss. So last night at 3 a.m., this is the list I came up with. Diego Redigolo helped me a little. Came up with a short list of anomalies from recent years. I'm sure there are tons more, so if your favorite anomaly is not here, just drop me a line, I'll add it. And we all know the drill. We have a bunch of, a few weeks before we start hearing some rumors, and we very quickly start chasing some anomaly. And it turns out that lots of papers come out. Half of them are roughly the same. Another fraction is totally wrong. And so you need to ask yourself, what is it good for? And it turns out that, at least I think, that very often we find that we have new ideas that come up in the ambulance chasing. So we have the whole community thinking about the problem, usually very different from what they were thinking about before. And new things come up. And those things have a life of their own even after the anomaly goes away. So just two examples is Dama, which is still kind of around, crazy anomaly. But one thing that came out of it was inelastic dark matter that we've all been studying. It got some more attention very recently, but it's a highly cited paper. It has a life of its own even long after Dama is no longer an ambulance to chase. Another example is Pamela that brought around this paper by this bunch of people. And in particular, they started discussing the hidden photon scenario, which was not new. It was in fact studied 20 years earlier. But if you look at the citations of the Holden paper from '86, so Pamela was in 2008. If you look at the citation paper, then you see that this series rise started in 2008, right after this paper. And it didn't just lead to extra citations. We've all been working, many of us have been working on the hidden photon since, and there's a whole experimental program going on. So there's a lot of activities, and these activities came about from this paper that was chasing an ambulance. So what do we learn from ambulances? It's a fun mental exercise, and it makes us usually abandon the vanilla kind of kinding principle that we are usually following. And when we do that, we look around and we might find new penguins that were otherwise overlooked. All right, so what I want to do today is give you two examples of such ambulances and the ideas that emerged from it. And there's a warning here. Lots of the things I'm going to talk about are work in progress. I'm not going to give you that many details. There's a disclaimer, which is those ideas might be wrong, and the results I'm showing you might still be incomplete. The positive side of that is that now that I'm publicly showing these results, maybe we'll be forced now to work faster and before we get scooped. The negative side is that we might get scooped. So the take-home message from this talk is please don't scoop me. Everything I'm talking about here is a work in progress. So if you haven't thought about it before, then please wait until we have our paper out. If you have, and let's talk about it in code. All right, so there's the outline. It's a little long. I doubt I'll be able to finish it all, but I'll just stop when I have to. I'll talk about the 21 centimeter anomaly and the Xenon 1-ton anomaly and the interesting things that I think can come out of it. And then we'll conclude. All right, 21 centimeter cosmology. Let me briefly remind you what that is. I assume many of you already heard and talks about it. So this is the history of our universe. There's these dark ages where after recombination, the hydrogen is neutral, and yet the universe is dark simply because there's no starlight. And the only light that there is from 21 centimeter spin flip of the neutral hydrogen. And towards the end of it, there's a reionization. This is called the cosmic dawn, when starlight shows up and reionizes the hydrogen. Now, people define the spin temperature, which is the ratio of excited versus a ground state of this hyperfine splitting. And there are basically three types of processes that can affect the spin temperature. There's the hydrogen-hydrogen and hydrogen-electron scattering. And what that causes is the gas, the hydrogen gas, to be coupled to the spin. Okay, so the spin temperature is roughly that of the hydrogen, of the baryons. Later on, as you go down in temperature, the spontaneous and induced emissions become dominant, and what that does is couple the spin temperature to the CMB. And once Lyman alpha, Lyman radiation shows up, so starlight, color temperature, what people call the color temperature, then you couple the gas, the spin, and this so-called color temperature as one bath, and so the spin just drops to the baryonic temperature. Okay. Now, by the way, if I'm going too fast, if you have any questions, just stop me at any time. All right, so there was this edges measurement that measured the so-called 21 centimeter temperature, which is basically the difference between the spin temperature and the CMB, and they measured it to be way below the expected value for standard model lambda CDM cosmology. Okay, so if that was the expected value, it's roughly 3.8 sigma away from it. And I'm not going to discuss the many possibilities for why this measurement might be wrong. And instead, I'm just going to chase the ambulance and ask, what do we learn if we assume this absorption line is real? All right. So one of the things that people have paid attention to is the idea that dark matter can cool the baryons. So what we need is the baryons for the baryons to be colder than what we naturally expect them to be. And if we have dark matter interacting with those baryons, then they can cool it down. The Boltzmann equation that describes it is written right here. We don't really need to pay close attention to it. There are three terms. One of them is just redshift. Another one is just Compton scattering of the CMB with the gas. And the last one is dark matter scattering that could happen. And dark matter scattering could have two different terms that affect it. One of them is just a scattering that acts to cool down the gas. And the other one comes about from the fact that the baryons and the dark matter can have relative velocities to one another, bulk velocities, and that those bulk velocities dissipate when they interact and act to heat up the gas. So there's a cooling term and there's a heating term, and two things come out of those terms. Number one, you see the interactions with the dark matter versus the interaction with Compton. In order to for the dark matter interaction to be effective, you need to beat Compton scattering. So you need a large cross section. So dark matter and the gas need to interact strongly. Second, if the dark matter is larger roughly than the proton's mass, then the cooling is just insufficient. And this stems from the fact that when the mass, as you dial up the mass, the density goes down, and so the heat capacity of the dark matter is not high enough, and you just don't have enough particles to cool down the baryons. So what you need is light dark matter. So you need large cross sections, light dark matter, which means that you need, what you would need is a cross section in order to be viable and produce a large enough dark matter cross section. You need the cross section that is velocity dependent. At the cosmic dawn, these are the coldest times in our universe before stars turn on, and as low as temperature as you can get. And so these are the lowest velocities that you get, which means that you can enhance the cross section significantly. So the most natural thing to consider is just v to the -4 Rutherford-like interactions. That means that you need long range force and a light mediator. But a light mediator has many constraints, as you know. And the question is, are these mediators screened or not screened? Okay. And one thing to consider are to see immediately is that unscreened long range forces are just completely excluded when you take into account fifth force constraints and cooling and so on. Okay, so these are just completely constrained, cannot explain the edges phenomena, at least not the way, not in the vanilla kind of way. And so what you need is something that is screened, which means that you do not interact with the hydrogen, and the main contribution just comes from the free electrons and protons that are still there at very small numbers, but still there. Okay, so you could go ahead and check what it is, and the natural thing to check is the hidden photon or a milli charged dark matter. Milli charge means that what I have in mind is pure milli charge without an extra degree of freedom, which would be the hidden photon. Both of them have very similar effects, slightly different constraints because of the presence of a hidden photon. And you see that in the end, there's very, very little region, small region here that may allow for the explanation of edges, but the bottom line is that it's unlikely to be the answer. Well, it was the case roughly, I guess, a year ago. So now what? Well, more recently, we came up with another idea to ameliorate the problem. So what is the problem? The problem is that on the one hand, the constraints from CMB imply that you cannot have too much of this milli-charged dark matter. Otherwise, because it interacts strongly with the baryons, it has strong impact on CMB. And what you need to do is to hide it in the noise, in the uncertainties for the energy density of baryons in the CMB. So for that, you need the density to be roughly below 0.4%. And so if the density is so low, then again, there's too little dark matter to cool down the baryon sufficiently. Again, you have a small heat capacity because you don't have enough dark matter. So here's an idea. What if instead we have two components of dark matter, the milli charge, which is it has a low density, and then the rest of the dark matter. And what if at early times, the milli charged dark matter is strongly coupled with the baryons, so that it hides it's part of the baryonic fluid, and it doesn't, it's below the fraction that that you can detect at the CMB, so it hides underneath the uncertainties. But then at later times, it couples more strongly to the cold dark matter bath. And so during those times, it can cool the baryons, and yet the heat capacity is much larger because you really have this CDM, the full dark matter bath that can cool the baryons through the milli charge. So that was the idea a year ago. And what we implemented it with is two couplings. between the Milli charge and cold dark matter and Milli charge and the baryons, both of them were Rutherford-like, going like v to the -4. But remember, the Milli charge only couples to the ionized electrons. This is this Xe over here. And the ionized fraction goes down very quickly towards after a recombination. And so if you look at the red line here, this is the ionized fraction, number of ionized electrons over the number of hydrogen atoms. And you see that if you go back in time at C and B, it's order 1, and then it drops very quickly. But once it drops, what that means is that this coupling over here between baryons and Milli charge drop. And so you couple, the Milli charge couple more strongly to cold dark matter. So this is this interaction. Cold dark matter interaction are dominant at late times, but are subdominant at early times. Okay, so that's precisely the picture that is drawn here. My Milli charge dark matter moves from the baryons to the cold dark matter. That's the idea, and you can try and see what it predicts. So the Milli charge dark matter itself can have a much, much larger parameter space, which is opened. So if you want this green line, so this green line over here is the standard Milli charge scenario. And now you can have a much lighter, a much heavier Milli charge, because the heat capacity comes from the cold dark matter, not the Milli charge itself. And you can have a much, much smaller fraction of Milli charge dark matter. You can go as low as 10 to the -8. So it opens up a whole new parameter space. Okay, there are all kinds of futuristic experiments that can probe it, neutrino experiments and so on, anything that is sensitive to Milli charge dark matter. And you can have direct detections going above ground and above the atmosphere. And so because this Milli charge dark matter interacts strongly, it doesn't penetrate the atmosphere. That's why all of the direct detection constraints, this is Sensei, end up somewhere around here. So this is Sensei above ground measurement. But you can take these measurements to the sky and try and look for this Milli charge dark matter. Interestingly, the cold dark matter itself, I mean, this scenario implies that the cold dark matter itself couples to electrons, because you just integrate out the Milli charge dark matter. And depending on the precise scenario, you have some predictions for the cold dark matter, which does need to be relatively light, GeV-ish, or below, in order to have a large enough heat capacity. So these are the constraints, and you would be able to probe them and constrain or find this cold dark matter with future Sensei and DAMIC and so on. DAMIC. So these are the prospects for this kind of scenario. So now the question is, what's next? So one thing that you could do is discuss Milli charge itself. There was a claim long time ago by these two authors that claimed that Milli charge particles are not around in the galactic plane. So let me just try and explain this statement, which is wrong. I'm claiming it's wrong. It's been claimed in the past few years that it's wrong. All right. So the idea is the following: charged dark matter cannot penetrate the galactic plane. Let me explain that. And I don't know if you guys know these books, but they're awesome. So I'm going to explain it at that level. So this is a ball. It's our galaxy, and it's roughly 100 kiloparsec. When there's a galactic plane inside, which is roughly 100 parsec, and there's a bulge, which is roughly, well, a little bit more, kiloparsec or so. And then there are coherent magnetic fields, which are aligned with this galactic plane. And the point is the following: if a particle comes in, then if its gyro radius is smaller than this 100 parsec, then it just gyrates and it can't penetrate the galactic plane. It gyrates around these coherent magnetic fields. So it just can't penetrate the galactic plane. At the same time, right, so this is the gyro radius, and it just tells you that you can't penetrate. So this is this line here. If everything above this line cannot penetrate the galactic plane if it comes from outside. But what about merely charged particles that started inside our galaxy? Well, you have supernova remnants, and supernova remnants are these blue things that have magnetic fields in them and they move. So when particles in the galactic plane hit one of these shock waves, one of these supernova remnants, they Fermi accelerate and they get enough energy. And if they have enough energy, they can just escape. So they need, in order to escape, they need to get a velocity larger than the escape velocity. At the same time, it can cool, those particles can cool because dark matter interacts with the electrons through this mini-charge, so it can also cool. And in order to escape, what you need is that the acceleration time is shorter than the cooling time. Now, we know one particle that hasn't escaped the galaxy, well, these are baryons. So we know that the acceleration time is roughly larger than 10 mega years. So you could plug those in, and what you find is that below this line, everything would be evacuated by the supernova remnants. So according to these guys, this whole region is describes a particle which would not be around us. In particular, let me stress this freezing line that you see here is one of the main targets for Sensei, for many other experiments, direct detection experiments. And we've been taking it very seriously, and we suddenly realized that maybe that's wrong. Are we missing something? And the answer is no. And the reason is that there are only not only coherent magnetic fields that are parallel to the magnetic plane in our galaxy. There are also coherent magnetic fields which are X-shaped. At least that's what is being claimed. And more importantly, there's incoherent magnetic fields which are factor of 2-3 larger than the coherent ones. And those incoherent magnetic fields imply that you diffuse in our galaxy. And so in order to figure out what's going on with merely charged dark matter, you need to solve these equations, which are these diffusion equations. And they're not very difficult to see what's going on here. You separate, this is a trick, a simplification of the actual true equations, but you can separate it into a slow moving and a fast moving component of the merely charged dark matter particles. And there's some diffusion, which depends on the rigidity and so on. And there's some cooling, which I mentioned before. Dark matter interacts with electrons. But then there's also these supernova remnants that can accelerate they can inject some spectra into the fastly moving component. And this can be worked out. And the interesting thing that you need to remember is that you have some time scale which takes into account two things. Number one is that supernova can't inject infinite amount of energy. They have a finite amount of energy and they can only inject so much. And how much of it goes into the dark matter which gets accelerated depends on some efficiency, which we don't really know what it is. So there's some parameter which is this efficiency. I'm going to call it kappa. Okay, so you can calculate this. This is work in progress. You can calculate the spectrum, and depending on the efficiency and depending on several other things, you get these spectra around us, and you'll see a cutoff here. And this cutoff comes about due to the solar winds in the sun. Around the sun, so anything with rigidity below GeV roughly will not penetrate. Okay, so bottom line, the take-home message. I'm going to get back to this plot towards the end, but the take-home message from that is that there are many charges around us, if it exists. There are lots of uncertainties which should be taken into account. We don't really know what are the magnetic fields, the coherent ones and the incoherent ones. What are these X? So these X fields are coherent and they don't align with the galactic plane, and they go way above the galactic plane, several kiloparsecs. So you could not place constraints on these models, but there are interesting predictions that you could look for. So that's the bottom line. And I'll get back to it when we get to the xenon anomaly. What's next? So far I described a model where both of these couplings were Rutherford-like. but you can ask, and we used the time dependence between the coupling, the time dependence of the bath, the 3 bath, due to this xe, the free electron fraction. But you could ask why have Milli charge at all? Maybe we can have just a different type of dark matter that mediates between the CDM and the baryons. So instead of Milli charge, you can have something else. And so you need models that are strongly coupled with the standard model. How much of it is viable? So there's a lot of work in progress that we've been working on here, but let me just show you one example. If you couple instead of a light hidden photon, you couple with a heavy hidden photon. So this would be a point-like interaction of what I'm calling Milli charge, but it's not really Milli charge, it's interacting dark matter with the baryons, with the electrons. Then you can get different predictions, both for the direct detection of the interacting particle and the cold dark matter. And these are viable. There's a lot of viable parameter space. There are several kinds of models that you could consider. We are working on these models. But there's interesting kind of scenarios to play around with. Here's wild speculations. There's the so-called Baryonyctaly-Fischer relation. The Baryonyctaly-Fischer tells us that the asymptotic velocities of rotation curves of stars that rotate around the galactic center have somehow know about the baryonic mass, right? So what you see here is the baryonic mass on the y-axis and the asymptotic velocity on the x-axis, and you see that they all sit on some line, which seems to indicate that the mass, that this asymptotic velocity is proportional to the 4th root of the baryonic mass. Now this is crazy, and it's a really surprising result, because according to standard theories, the mass here, the velocities at the edge of our galaxy should not know about the baryonic matter in the center, because you're completely dominated by the halo, dark matter halo. So what it suggests maybe is some correlation between the dark matter and the baryons. And you need strong correlation at some point. And so one question to raise is, could it be that these Milli charged particles that interact with both baths mediate this kind of information between and allow to cool the or correlate the baryonic mass and the dark matter mass? So wild speculation. We are just thinking about it. I have no idea yet whether it can work or not, but you could imagine why it would. All right. So this is the temperature evolution in this scenario. When you see the orange here is the Milli charged particle, and it starts by being correlated with the baryons, as we discussed, and at later times it starts, it moves and goes into thermal equilibrium with the cold dark matter. And this coupling here, right, this transition here can correlate in principle between the baryons and the cold dark matter that would later produce these asymptotic velocities. And of course, everything then couple again, because at some point the whole dark matter virializes, and once it does, you have the velocities go up again, and so you could imagine that once again the Milli charged dark matter, the interacting dark matter, couples back to the baryons rather than the cold dark matter. So there's a whole story to consider here. Structure formation could be well affected. It also depends on the distance from the galactic center, because the virial velocity depends on radius. And so there's a whole story to study here that is could be exciting. All right, so I'm going very fast. I hope that's fine. Again, stop me if not. Let me move on to the Xenon-1 anomaly. How much time do I have, by the way?
You have like 5 minutes or so.
All right, 20 minutes. That's fine.
Five.
Yes, I do. No worries. Okay, we'll see how far we go. So the Xenon-1 anomaly, bottom line, Xenon just measured electron recoil events, and they see some excess of events between 2 to 4 keV. It could be an excess anywhere between 2 to 3.5 sigma, depending on what you actually measure. what you fit. But it got the community excited that maybe something is going on here. So if something is going on, it could certainly, we heard a little bit about it 2 days ago. Of course, it could be backgrounds, but again, we are all about chasing ambulances. So let's just assume this is new physics and ask what can it be. And I'm going to run really quickly with the things that have been discussed. Bottom line, what we need is excess around 2 to 3, 2 to 4 keV. We cannot have an excess at lower energy because there's the xenon 1 ton S2 only analysis, there's sensor analysis at even lower energy, and there's no excess there. So whatever new physics you have needs to be focused on this 1 to 4 keV. And you need to evade the star cooling constraint, you need to evade dark matter nucleon constraints, and so on. If you want to consider absorption, which is an interesting scenario, it could be a scalar, it could be a vector, and it could either be dark matter or just produced at the sun, okay, solar. So I'm not going to go through all of this because it's going to take too much time, but let me just point out that you could study dark matter for the photon dark matter, scalar dark matter, or Alp dark matter, axion-like particles. Dark photon is relatively viable. The scalar is excluded, and it's excluded by star cooling. This is the horizontal branch and the red giants. And Alps are strongly model dependent. They are by and large excluded unless you have some UV complete model which allows you to evade X-ray constraints. So you need some specific UV model, and then you can live with this, explain this excess. Okay, so I'm not going to go through the physics here, but it's possible, but model dependent. What about solar bosons? Well, the production of solar bosons in the sun is all peaking at high energy, unless either you're talking about axions which couple to photons, and then you see this is the Primakov effect, and it goes down at low energy, or you have a massive axion around the keV, and then this cuts off the production at low energy. Okay, and remember, you want to cut off production, otherwise you're going to be excluded by the S2 only analysis at xenon or the sensor analysis and so on. So again, you can do it. You can have a photophilic and a photophobic dark matter, solar axion, sorry, not dark matter. And bottom line is that all of them are excluded, again, because of the star cooling. So this is just dead. And you could also do solar scalars, and I'm running here again. It's excluded by solar cooling, and you can try the dark photon, and again, it's excluded by star cooling. So you could ask, is this the end? And the answer is no. You could play around with the idea of having a field which is chameleon-like. So chameleon means that its potential depends on the environment, and the environment in these stars is very harsh. In red giants and white dwarfs, you have a very large density, much larger than the Earth, and certainly and the Sun. And so the Earth is 2 orders of magnitude even below the Sun, roughly. And so just as an example, you could have, to explain how it works, you could have, let me show you how you have Chameleon Alps. So Chameleon Alps, just imagine that you have 2 more fields, S and X, and one of them I'm going to call the symmetron, the other one is the Pecha Queen guy that is going to produce the axion for us. So there's some potential for S, which produces the axion, the usual stuff. And there's a symmetron field, which depends on the density. If the density is large, then the mass here is the overall mass is positive, and the VEV for X is 0. And if the density is low, then X gets a VEV. Okay? And now you couple the 2 fields together to electrons. You can do it through Forgat-Nielsen-like theories and so on. And once you do that, what it implies is that at high densities, you cannot decay into the VEV is 0, and therefore you cannot decay into electrons. You cannot be absorbed by electrons. But at low densities, you can. Okay, all kind of constraints that you need to take care of. Let me not go through them because we don't have time, but this is the bottom line. There's a regions of parameter space which are fine. If you want, you can look either at, so the one model is this model here with the constraint, which is this green region here. This is called the solar basin. It's an interesting new constraint which discusses how this particle can be produced and be caught in around the sun, and this constrains the scenario of having axions that are produced in the sun. So you can evade this constraint by suppressing the production a little bit in the sun while keeping the rate that we measure in the Earth, and so you could have the constraint around here and this whole region that explains the xenon anomaly. So it's nice. All right, other chameleon models exist. Now here's the last in the last maybe 3 minutes. Let me explain very briefly what can you do with it. Where can you take it further? So what did we learn? We learned that Chameleon Alps, sea Alps are not particularly interesting, but you could do it, and if you wanted to, if you believed in the ambulance. But if you remember that this could only be an ambulance, then Chameleon Alps are not particularly motivated. But we can examine new type of models that are relevant for direct detection and all kind of mediation schemes, production mechanism, and so on. And the point is that up until now, we've mostly been discussing mediations through light vectors or point-like interactions. And you could ask yourself, why? Why only light vectors and nothing else, especially for direct detection? And the answer is stellar cooling constraints. So if you look at plots that were studied long ago, you would find that, if you have a hadrophilic scalar, a leptophilic scalar, a B-L vector, all these are just dead due to star cooling constraints, okay? And there's very little chance of measuring them in direct detection just because of cooling constraints. So can you have instead a chameleon mediator? So you have mediators that connect between the dark sector and the standard model, okay? And here's a very, very simple scenario. Just again, this is work in progress. Very, very simple scenario. You have two fields. One of them is just the mediator, it's phi, and the x again is going to be a symmetron. So the x is again gets a wave or doesn't get a wave according to the density in the standard model. Phi itself gets some wave, has a wave, and it couples to the dark matter, it couples to the electrons, for instance, but you'll notice that it couples to electrons through phi squared, okay? So the coupling is highly suppressed by 1/m squared, unless, for whatever reason, phi gets a wave. So if phi gets a wave, as it is right here, then everything is fine. You plug it in and you get this stronger coupling, larger coupling between phi and the electrons and phi and the dark matter, and so there's strong mediation. However, we now turn on some coupling dynamics inside this chameleon mediator sector, which can influence whether phi gets a wave or doesn't get a wave. Okay, it's like a waterfall field if you want. And bottom line is, in the Earth, phi doesn't get a wave, which is why we get scattering, but in stars, x gets a wave and then phi doesn't get a wave, and you suppress productions. Okay, and these are the plots, again, preliminary, and you could see, just look at the right, for instance, some chameleon mediator. You see that we've opened up significant part of the parameter space. The freezing again is alive, and these would be the usual type of constraints, and these are the new constraints, depending again on the precise model. Now this is interesting. You could try, this was a weakly coupled example. Really, to generalize it, I think is even more exciting, because what you really want to do is do something like general dark mediation. You have operators that couple, you have currents between the standard model and the mediator sector, and the mediation sector and the dark matter, and all you care about are currents. And in strongly coupled theories, really what happens is that those densities affect the anomalous dimensions of these currents, of these operators, and can change the effective coupling. So there's a whole new language to discuss here through chameleon mediators. And there's a lot to discuss. You get very different dark matter form factors. You have different production. You could have different production mechanisms. So there's a whole family of models to discuss, which go way beyond just the hidden photons that we've been doing, or point-like interactions. All right, I'm going to skip the scattering, and I wanted to discuss one more work in progress, and just one last two more slides, which are the Milli charged again. So this we've seen already. This is the Milli charged dark matter with the and I've mentioned that there's this cutoff because of the solar wind. But remember, so you get this spectrum, which is cut off at roughly at a KV energy, and KV energy is exactly what you want. So if you want to look at this plot again of the edges, and this is the Milli charged dark matter scenario, in order to explain Xenon 1 tan, you need the kinetic energy to be around a keV, and you need the momentum, so the rigidity to be larger than a GeV, the momentum over the charge to be larger than a GeV. Otherwise, you don't penetrate the solar wind, the sun. So these two together draw a line here. So here, this whole region will not be penetrated. Now, on the other hand, you also want to make sure that the velocity, you could only get large velocities, you cannot get small velocities. So dark matter needs to be with velocities of 10 to the -3 or above. That's the spectrum. And so this whole region requires dark matter to have velocities way too low. So you have a whole new region here that can actually explain, with Milli charged dark matter, can actually explain the Xenon 1 tan anomaly. So this is work in progress. I really hope that we'll have a paper out in a week or two about that. All right. So there are possibly other interesting predictions that I won't talk about here, but there's lots to do with these Milli charged games. All right. So let me conclude, because I think I'm out of time. So I think our job is to explore new theoretical possibilities and develop new experimental directions. That's the main thing that we need to do in order to find new physics, and may as well have fun while we do it. And anomalies and ambulances boost this process. We are thinking about the problems together. We let go of the usual kind of standard vanilla thinking, and we think out of the box. And so we identify holes, we motivate new experimental directions, and it's fun. So my only comment is that you should choose your ambulances with care. And I'll stop here. Thanks.
Excellent. Thank you, Tomer, for this super nice talk. So I guess there are plenty of questions or comments for Tomer. So I have one mini question, just out of curiosity. When you, in many times in your plots of Milli charged dark matter, you have this constraint called labeled evacuation from the disk, sorry, that corresponds to what you say, that Milli charged particles are not able to enter the disk. I was kind of confused with that.
No, so my point was that
exactly there. For in next slide.
Here.
That.
Yeah. 1 second. So that was the old claim that this region here is excluded because you just can't, above this line you get evacuated, and below this line you cannot penetrate back. So that was the old claim by Corbetal, and it's not correct. So it's not a real. This is not a real constraint, and that was the point. The next point of what I was discussing, which is coherent magnetic field. Yeah, I went a little fast there, but that was the point. You do have these constraints just don't exist because dark matter can penetrate, because you can diffuse into the galactic plane. Despite the coherent magnetic fields, you can diffuse into the galactic plane. And so the spectrum that you get around the sun is the thing I was showing before. Let me show you. Yeah, this is it. Yeah, so that was the spectrum. You actually get it above the atmosphere. We still need this is a calculation without the penetrations through the atmosphere and the Earth for direct detection. So we're doing that. But so the usual shielding for strongly interacting dark matter. But yeah, there's definitely there could be milli-charged dark matter in the galactic plane. Yeah, that was the bottom line from this diffusion thing.
Okay, see.
Can I ask a follow-up question to that? I think you probably already said this, but how sensitive is this to the magnetic field model? Because you said you could add these X's and there's a lot of uncertainties. So how much could these lines change?
Oh, I think so. I don't know. I can't tell you. I don't know the final answer because there are lots of uncertainties, and it depends how you model these uncertainties. For instance, this X field, which people have not been paying attention to, and I think there's still some debate whether they exist or not. It's consistent with what we see in other galaxies and so on. But you know, these are coherent fields that go all the way to the center of the galaxy. So now, how do you model that? It's, you know, okay. How do you model that? You could model it just by putting, you know, you're doing your diffusion in a box, and you could just model it by putting the right boundary conditions on the galactic center. But even that is a toy model. It's nothing like what we actually believe is going on. And you know, so Farrar et al. Are doing these fits for these magnetic fields, and I think they're very sensitive. The fit is some funny function which is very sensitive to the assumptions you make. So I think the uncertainties are large. It's very hard to estimate how big these systematic uncertainties are. You should also remember that even knowing the stochastic magnetic fields is difficult because
and like what is the size of the X's like compared to the stochastic field? Several orders of magnitude.
So you mean,
different.
Yeah, so in terms of the magnetic field itself, it's roughly the same.
Oh, it's yeah. Okay.
But you know, the X shape can bring you in directly into the galaxy from the outside because they extend like 5 kiloparsec and even more above the galactic plane. The galactic plane is 100 parsec. So they extend way up and they can just draw you in. You know, if you sit on those lines, you could just go directly in. You penetrate it without any problem. You don't need to diffuse. And then the diffusion would go along the parallel direction rather than the perpendicular direction with respect to the galactic plane. And you know,
so would there be like a preferred direction? Yeah, a preferred direction for these particles? For I guess the diffusion would the diffusion would erase that.
Well, the diffusion. So now that you need to ask yourself, how well do we know the diffusion coefficients for the parallel field and the orthogonal fields? And even that, I think we know to some extent, but not well enough. There are uncertainties even there. So we've been long ago when we started working on this, we were playing a lot with it. Remember also that we measure cosmic rays and the diffusion coefficient in one region, and then we do Monte Carlo and simulations in a different region, which we care about here, for different rigidities. Yeah, because the Q, we are talking about charges that are very small, which means the rigidities are very large, and those are not the regions where we actually measure the incoherent magnetic field, the diffusion. So there are large uncertainties. Whether we even know how to model them well, to model the uncertainties well, I don't know. It's a hard problem. So I would not trust. There was a paper, Keisuke had a paper a while ago where he was placing constraints on these milli-charged, Keisuke and Lawrence Hall and others, and I wouldn't trust these at all. I wouldn't trust. There are no constraints. There are so many uncertainties that to say that these are you can constrain milli-charge this way, I think it's a bold statement. I would more consider the predictions that we have and see whether we can go for them. I'm wondering. I don't know, But even the freezing line, how well are we going to probe it, because the fraction of the milli-charge might change, right, according to how well you diffuse. So I really don't know. At this point, I don't know. I can't tell you that we probably in the upcoming paper will probably not study all of the uncertainties. We studied a few of them back a year and a half ago. We never published it, and we need to get back to it. So there's lots to do. There's lots to do.
Sorry, Tomer, a very naive question here from Stefano. So, the X-shaped field is coherent, and so it should not contribute to the diffusive properties of these particles, but only to the energy losses. So that's,
it could also allow particles to penetrate through the along with the coherent magnetic field. That's what I'm saying. So if you have this X field and you come from the outside, you can gyrate around.
Well, I don't know, because this is still a diffusive process, isn't it? So in other words, the incoherent component would screw up your gyration and the trajectory of the particle. I don't think you can you can say that you have both that preferred direction and the diffusive process. So it's kind of
right. So it depends. So now you're talking about the modeling. We simply don't know. That's what I'm saying. It's not obvious to me that I agree with you that it's not completely obvious that you can penetrate, but it can certainly help you. And the statement that you just you really need to diffuse from the top of your galactic plane, that's far from obvious to me, because there are regions, if you look at the fits that they do, Johnson and Farrar, you'd see that there are regions where, especially close to the galactic plane, the galactic center, where this X shape dominates, and then you could argue that at least some fraction can go along this magnetic field. So
at least for the cosmic rays, the role of coherent magnetic fields is essentially to trigger energy losses through the synchrotron more than anything else. But yeah, I don't know. And another question, Tomer, is Tomer still there?
I hope so. I think he got disconnected.
Yeah, sounds like it. Oops. Well, perhaps we can actually move to the discussion part of the